Okay, welcome everyone. Good morning, good afternoon, everyone. I'm Silvio Savarese. I'm the director of the Stanford Vision and Learning Lab. And today I'm going to present, I'm going to give you my overview, my insights in terms of trying to discuss how smart, how intelligent are the current perception systems and some relevant applications to perception systems. So AI has been, the field of AI, artificial intelligence, has been a major propelling force of today's technology and societal changes. And within the field of AI, machine vision has made tremendous progress in the past 10 years. So for instance, computer vision and natural language processing are dramatically improving the quality of systems for image recognition and classification. And examples are the Apple's Siri, Google Photo Organizer, Facebook Face Recognizer. In retail, robots are used to improve the efficiency of warehouse and organize, retrieve products. An example is the Amazon Kiva system. In healthcare, image recognition technology can improve the accuracy of the diagnosis of several diseases, including cancer. And corporates and hospitals are pushing programs for smart healthcare and early diagnoses. In agriculture, farmers and seed producers can now utilize machine vision techniques to improve crops yields and automatically assess the quality of the produces. And this has become a recent area for investment. So why is these accelerations happening now? Well, it is happening now because this is thanks to a number of critical enabling factors. One is better algorithms based on deep learning technology, as most of you already know. And this allows to learn from examples rather than rely on predefined rules. Larger and larger repositories of data, which allows to train those algorithms at the level of accuracy that is desired for applications. Faster and commoditized hardware, for example, GPUs and FPGAs, which makes training efficient and scalable. So all these enablers have made it possible for computer vision technology to achieve a number of breakthroughs. So for instance, algorithms can now accurately associate pixels to label and identifying objects as bounding boxes or segments with a high degree of accuracy. Moreover, state-of-the-art 3D vision techniques can now be used to obtain accurate metric reconstruction of the environment. This is an example of a 3D reconstruction of the Gates buildings at Stanford performed by my own students. And such 3D reconstruction can be further processed into semantic components. In this example, 3 points are associated to different color codes, which corresponds to, to different object classes. This would allow an agent, for instance, to navigate and look for items or places of interest. So thanks to all these factors, it appears as if AI is just a few steps away from transforming our lives and enabling scenarios where smart homes, smart cities, assisted robots, and autonomous cars are become a reality. But are we there yet? And not quite. So we argue that despite all these achievements, AI-driven technology is still far from achieving the level of accuracy and reliability that is needed for all applications I mentioned before. And here are some recent examples of failures. So for instance, the accent of a self-driving car designed by a known manufacturer. The accident resulted into a casualty in the summer 2016. Here, an example is the robots that have a hard time opening a door during the latest DARPA Grand Challenge in 2015. And a security robot that accidentally attacked a child in a shopping mall at the Stanford in 2016. So where did it all go wrong? And I want to argue here that the majority of reasons for failure are due to a number of critical limitations of the perception system. And let me elaborate on this and give a few more examples. Suppose that we have an autonomous car that needs to figure out what's ahead. What the current methods in machine vision supply is a bunch of bounding boxes. So 2 people, a building, a road, and in this example also a strawberry shows up, and also another big strawberries on the next to it. So can you tell what's going on in the scene based on these bounding boxes? It's very hard, right? So it's very hard to understand what's going on. But that's exactly the type of input that those machine vision systems supply. That's actually the actual scene. So in fact, bounding boxes and labels tells you the objects, where they are, but they can provide an integrated interpretation of the scene. And in fact, it's really the actual, it's really the context and the complex interaction of objects and space that makes the story of this image. However, modeling context is very hard. Then let me show now another example. Suppose that the robot needs to go to the house back there, and what again is going to see is the number of boxes, bounding boxes. A woman facing right, another woman facing right, a chubby old man on the back, another woman on the left, a man on the left. Okay? And the question here is the robot needs to decide whether to go to the left, to the right, or to the left in order to get to the house. So which path would you take, right or left? Well, probably the easiest answer will be let's try to get the shortest path, right? Well, let's see actually what these bounding boxes are telling us. Again, only when we see the story behind the scene, the robot can make an informed decisions. Here, a kid is about to receive a toy from Santa Claus, and the people on the right are talking to each other and don't care about Santa Claus. So even if the shortest path is the one on the left, eventually the robot needs to take the path on the right because this would be the one that wouldn't bother Santa and the kids that are interacting with each other. Again, this is about situational understanding, but the problem is that situational understanding is often guided by rules of conduct that are vague and non-verbal. And these rules often depend on the etiquette and social conventions. For instance, interpersonal distance changes depending on whether two people are friends, spouses, family. And this is true whether we talk about humans or cars or urban traffic in general. The point here is that all these non-verbal rules that regulate interactions and interrelations are very difficult to model mathematically. And the question is how to encode those mathematically, and in order to, for instance, encode the fact that Santa Claus is not supposed to give a gift to a toy without interfering to it. So the field of AI is still far from achieving this kind of results. As a final example, let me go back to the story of the robot that attacked the child. So let's examine the event in a few more details. So during the past summers, in a shopping mall in the Bay Area, a security robot took out this toddler. And the robot is 5 foot tall, 300 pounds heavy, and equipped with nearly 30 sensors. It's a surveillance robot made by a startup in San Francisco. So what happened? According to witnesses, a kid bumped to the robot and fell forward, dropping a toy that he was holding. And allegedly, as the kid tried to reach this toy, the robot ran over it. The good news is that the kid didn't get hurt, but still it was a bit of a disturbing event. So these are the so-called corner cases. That is, unusual events, difficult to anticipate, but that can have potentially catastrophic results. And the idea is that it's true that operating in the real world does mostly entail repetitive tasks, but also includes an endless supply of corner cases, potentially deadly corner cases. And because these corner cases are rare and always different, it's difficult to gather data to train those models, understand and predict them. This is where big data and deep learning fail. And this is confounded with the fact that current systems have a hard time addressing high degree of uncertainty in the environment. And failure to do so can lead to catastrophic events like the one I described earlier. So in this case, the robot was not aware of the fact that he was not confident about making a decision. So it's critical to achieve rigorous evaluation and management of risk in order to design systems that are reliable. So to summarize, even if machine vision has been successful in uncovering 3D information, 3D geometry, associate pixel to labels, get the semantics out of scenes, out of images, today's robotics perception is still far from the kind of coherent and complex interpretations of a scene that humans are capable of. And this is because current systems still have a hard time in reasoning about context and achieve situational awareness, have a hard time capturing non-verbal rules and model social etiquette, and finally model corner cases and manage risk. And achieving these goals will make AI systems capable to read complex situations and respond to them in an appropriate way, similar to what humans do. So this has been a major effort in my group research over the past few years, and in the remaining portion of this talk, I'll discuss how to achieve some of these goals in the context of our work on object recognition, scene understanding, and activity understanding and prediction. So let's start with the first one. So our work on object recognition has focused on the problem of characterizing objects in terms of their semantic and physical properties. This essentially means that given an image like the one we see here, which were never seen in training before, we don't just want to associate pixel to a bounding box, like this one shown here, but also to discover object properties like parts, functions, shape, and pose. And this makes images of objects actionable and let an agent to interact with it. In these examples, red boxes indicates the chair's parts, and the yellow box indicates where the area where the agents might sit. And similar example here for the table, for the bed, and for the cups. This is the area, the yellow area is the area where the agent will need to interact with if he wants to grasp this cup. In the recent work, we demonstrated that the concept of smart cups and smart dishes. Here, a smart cup senses the presence of a person and adjusts its positions and pose in order to be grasped more conveniently. This was possible by inferring the way a cup can potentially interact with the hand. That's the secret sauce here. It's actually, the smart cup is essentially a robot on wheels on top of which the cup is mounted. And thanks to camera systems, we can make the cups to interact with the user in automatic fashions. This technology can enable a new generation of smart appliances in the context of smart houses and IoT. So now let's talk about scenes. My students have looked at the problem of obtaining an integrated and contextualized understanding of the scene from images, from various sensing modality. So given an image of a scene like this one, we don't just want to describe it as a collection of bounding boxes, but rather make sense of the perceived environment in terms of objects and the context, in the context of 3D environment. So we have shown that it's possible to process large-scale 3D-point structures like this one. This is the first floor of the kids' building, and in turn turn it into informative and functionally meaningful buildings elements called building information models, or BIM. Building elements include, for instance, corridors, rooms, hallways, which are shown here with different color codes. But in turn, this can also be parsed into smaller, fine-grained semantics, such as walls, tables, windows, and so on. And the key innovative aspect of this work is that the BIM parsing are evaluated at the presented large scale, following a procedure that is fully automatic and hierarchical. The ability to parse building elements can play a role, a critical role in many applications. For instance, one is automatizing large-scale information management and for construction monitoring and verification. The idea is that given a construction site like this one, we can compare our BIM, the one shown on top left, with an S-plan model shown on top right, which includes what is expected to be constructed at any given day, week, and months of the construction work. And this comparison allows to automatically predict the elements that are constructed on schedule, ahead of schedule, and or behind schedule, which are shown here with different color codes. This process can be done at any given day, week, and makes the verification easy, cheap, and objective. It has been estimated that automatizing the verification process through an AI system shown here, like the one shown here, can lead to savings in order of billions in the construction business. Let me now conclude by bringing the people in the picture. In my group, we have looked at the problems of understanding and predicting the behavioral agents in complex situations. As we discussed earlier, modeling scenes by isolated labels such as standing, sitting, looking right, looking left doesn't bring us very far. In fact, by only considering the interrelation among objects, people, and space, we can get better sense of what's going on in the scene. In this case, these three people are not just standing, but actually are in a queue waiting for food. These people are not just sitting, but having a meal, and so on. And it's really the complex interactions among objects that makes out the story of this image. So my students and I have introduced methods that can process video sequences like the one here and recognize activities such as talking, waiting in a queue, ordering food, and so on. This allows to achieve situational understanding in complex scenarios like the one shown here. And critically, This is done by automatically capturing and inferring non-verbal rules that regulate the target interactions. And here we show some examples of those verbal rules, non-verbal rules. So our methods for discovering patterns of social interactions is a key component of the brain of a new robotic platform which we have been developing in my group called JackRobot, which is shown here. And JackRobot is mounted on Segway and is filled with sensors such as LiDARs, cameras, GPS, and so on. And the goal of JackRobot is to navigate in pedestrian environments like a building or university campus or shopping mall or a train station or an airport. But its goal is not just to navigate and avoid bumping into obstacles, but also to be amicable, interactive, and react appropriately to the unwritten rule of pedestrian traffic. In this example, JackRobot senses the 3D environment and detects the tracked pedestrians. The orange line here is the planned trajectory that the current estimated, given the current estimated collision map, shown here. And as pedestrians populate the scene, JackRobot updates its trajectory by taking into account the predicted target trajectories, as well as the social forces, the social interactions relating those targets. This work has still large interest in the robotics community, has also received a substantial amount of news coverage in the past few years. Okay, in conclusion, I would like to, I hope that I convince you that in order to achieve true visual intelligence, one needs to find a way to reason about functions, context, and common sense, achieve situational awareness, capture nonverbal rules, and critically handle corner cases. And I would like to thank students and researchers in my group that have been working hard on these problems, as also our sponsors. And before concluding, I would like to share with you the fact that some of these ideas are now a key ingredients of a new venture called AIB. AIB was founded just a few weeks ago by a veteran in the AI industry, Yanqin Lin, former head of research at Baidu. And AIB is now, it's a new AI to business startup. Its mission is to provide AI solutions for upgrading and transforming industry verticals. And as such, AIB will provide breakthrough technology within the entire spectrum of AI, including vision, speech, NLP, data analytics, and so on. And this is a kind of a new exciting venture, and I will work in close collaboration with Yanqin and the AIB team in the future. We are now hiring AI talents, so if you want to learn more, please don't hesitate to reach me out. And with that, I would like to conclude. Thank you for your attention.